Welcome. To understand the true nature of UY Scuti, we must first accept that our human senses were never designed to perceive the reality of the cosmos. We live on a planet that takes days to traverse, a world that feels vast and permanent. Yet the moment we leave our atmosphere, it becomes clear that we are residing on a tiny, fragile speck within a colossal universe that operates on scales we simply cannot comprehend. We look at the night sky and see thousands of tiny pinpricks of light, and because they all look roughly the same to the naked eye, we assume they follow the same rules as our sun. But those lights are lying to us. Some of those dots are individual beasts that, on their own, defy our understanding of scale and break every intuition we have about what a star is even supposed to be. For years you have been told that UY Scuti is the king of these monsters, the largest star ever discovered, but the documentaries you've watched are missing the most terrifying parts of the story. They show you a solid glowing ball of fire, but they ignore the massive lore gaps that suggest UY Scuti is not just a big object, but a scientific paradox, a star that shouldn't exist according to our best models. The first great gap that your competitors have completely ignored is the envelope illusion paradox. Most documentaries treat the surface of UY Scuti as a definitive physical boundary, a hard edge where the star ends and space begins. They show you animations of a ship flying over a roiling sea of plasma, but this is a fundamental misunderstanding of the physics at play. In reality, UY Scuti's outer layers are millions of times less dense than the Earth's atmosphere. As you approach this titan, you wouldn't find a wall of fire. You would find a glowing fog so diffuse that it is less like a solid sphere and more like a light-polluted cloud of gas and dust being blasted into the void. If you were to fly a Boeing 777 at its normal cruising speed around the circumference of this star, the journey would take you more than 1,200 years. But for a vast portion of that journey, you wouldn't even realize you were inside the star. You could travel thousands of kilometers through what we call the photosphere and still see the distant stars of the Milky Way through the thin, superheated haze. This star is so incredibly empty that its volume is 10 billion times that of our Sun, yet it is barely held together by a gravity that is losing a war against its own internal light. This is the illusion. We are not measuring a solid kingdom, but a star that is essentially a cosmic accident, a massive amount of matter that has ballooned outward because it can no longer contain its own energy. This leads us to the second massive gap that the standard scripts fail to address, the stellar cannibalism mystery. Astronomers are currently scratching their heads because UY Scuti shouldn't be this large. There is a theoretical boundary called the Hayashi limit, the point where a star becomes too large to remain stable given its mass. If a star crosses this line, gravity is supposed to win, pulling the star back in and making it smaller. But UY Scuti is scraping the very edge of this limit, and here is why that is a mystery. While it is 1,700 times wider than the Sun, it only has about 7 to 10 times the Sun's mass. It is an impossible balloon. A star with such low mass should not have enough gravitational glue to grow into a hypergiant of this scale through normal evolution. The hidden lore suggests a much darker origin story. UY Scuti exists in a region of the Scutum constellation that is incredibly rich with massive stars, suggesting it was born in a dense, crowded stellar nursery. The stellar cannibalism theory posits that UY Scuti didn't just evolve, it feasted. It may have achieved its record-breaking radius by merging with nearby stellar material, or even swallowing smaller companion stars during its early, violent years. It is a Frankenstein star, a behemoth built from the remains of its own solar system, using the mass of its devoured siblings to inflate its outer layers to the orbit of Saturn. But even if you could survive the cannibalistic hunger of its birth and the ghostly fog of its surface, you would run into the third law gap, the habitable zone nightmare. One competitor might mention that a planet could survive 1.5 trillion kilometers away from UY Scuti, at a distance of about 1,000 astronomical units. They describe a world where a single year takes 10,000 Earth years, and where entire civilizations could rise and fall without ever seeing the seasons change. But they are ignoring the pulsation chaos. UY Scuti is a pulsating variable star, which means it doesn't just sit there, it breathes. On a cycle of roughly 740 days, the entire star expands and contracts in chaotic, violent rhythms. For a planet in the so-called habitable zone, this is a death sentence. The star's surface pulses so dramatically that it could literally swallow its own inner planets and then spit them back out as vaporized dust. Because the star is so unstable, it is constantly throwing off its own mass in violent burps, ejecting the mass of an entire Jupiter into space every few years. These eruptions create a surrounding nebula, 10,000 astronomical units in length, a graveyard of gas that would obliterate any atmosphere on a nearby world. There is no Goldilocks zone here. There is only a shifting front of lethal radiation and stellar winds. This is the version of UY Scuti that the standard leaderboards don't want to show you. It is a star caught in a measurement war, where the newest data from the Gaia spacecraft suggests it might be a fallen noble, much smaller and closer than we previously believed. We are looking at an object that is 9,500 light-years away, meaning the light we see tonight left that star when human civilization was just beginning to learn how to farm. Because hypergiants like this have such short lifespans of only a few million years, there is a terrifying possibility that UY Scuti has already exploded. The death signal of its hypernova explosion, a blast with the power of 100 supernovas, could be racing toward us at this very second. When it arrives, it will outshine entire regions of the Milky Way, signaling the end of one of the universe's greatest spectacles. But until that light reaches us, UY Scuti remains a ghost story written in the stars, a titan of nothingness that challenges everything we thought we knew about the limits of the universe. We aren't just looking at the largest star, we are looking at a cosmic anomaly that is tearing itself apart before our very eyes. To understand the scale of what we are about to face, we have to start with something small, something you can hold in your hand. Imagine a tiny peppercorn, just 2 millimeters wide. In the grand theatre of our minds, let that peppercorn represent the earth, everything you have ever known, every mountain you've climbed, every ocean you've crossed, and every person who's ever lived, all contained within that 2 millimeter speck. Now place a standard football on the ground next to it. That football is our sun. It is 109 times wider than our earthly peppercorn, a glowing orb so massive that more than 1 million Earths could fit inside its volume. Even if you gathered up every planet, every moon, and every asteroid in our solar system and piled them together, the Sun would still be 743 times more massive than all of them combined. For us, the Sun is the ultimate definition of large. It is the anchor of our existence, a fairly average G-type main sequence star that has powered life for billions of years by converting 600 million tons of hydrogen into helium every single second. But as we prepare to leave the familiar comfort of our home, you must realize that in the kingdom of the universe's giants, our Sun is nothing special. It is merely a modest spark in a quiet corner of a galaxy that is filled with beasts that defy our understanding of scale. We are about to embark on a journey that the human mind is fundamentally built to resist. We are climbing the cosmic beanstalk into a realm where our intuition breaks. To begin, we must move at a speed that makes even the fastest human technology look like it's standing still. Think of the Voyager probes, the fastest objects humanity has ever launched, or any probe currently drifting through the void. At their speeds, reaching even the nearest star would take tens of thousands of years. So we must move faster. We must travel at the speed of light, 186,000 miles per second. At this speed, you could circle the Earth 7 times in a single heartbeat. You would cross our solar system almost instantly. You would pass the Alpha Centauri binary system in just over 4 years. But even at the fastest speed allowed by the laws of physics, the journey we are taking is so vast that space itself starts to feel like an ocean of nothingness. We are drifting 9,500 light-years away from home, toward the southern constellation of Scutum, the Shield. As we move, the Sun begins to fade. It becomes a dim spark, then a flickering point of light, and finally, it is swallowed by the dark, lost among the 400 billion other stars that call the Milky Way home. We are heading deep into the Cygnus Rift, a challenging region of the galactic plane obscured by thick, dark bands of interstellar dust and gas. This is the zone of avoidance, a place where the light of the galactic core drowns out the objects around it, hiding the universe's most monstrous secrets from our telescopes. We are traveling so far that by the time the light we are seeing tonight actually reached your eyes on Earth, entire human empires had risen and vanished. Languages were born, flourished, and were forgotten while these photons were still mid-flight. And there, at the end of our 9,500-year-long light trail, we find it. UY Scuti. At first it appears as a faint, somber red dot. It doesn't seem extraordinary until you begin to peel back the layers of its reality. UY Scuti is a red hypergiant, a star so impossibly large that it stretches the very definition of what a star can be. To truly comprehend its size, we have to perform a cosmic experiment. We have to bring this titan home. Imagine replacing our Sun with UY Scuti right now. The result would be a cosmic catastrophe in slow motion. The moment UY Scuti takes the place of our Sun, the surface of the star, the photosphere, would not just sit where the Sun is. It would instantly swallow Mercury. It would erase Venus. Our peppercorn Earth wouldn't even have time to burn. It would simply be dissolved into the superheated plasma of the star's outer layers. Our entire history vaporized in a fraction of a second. But the Titan doesn't stop there. It continues to expand, deleting Mars and engulfing the entire asteroid belt. Every rock, every fragment of our inner solar system wiped out. Even Jupiter, the undisputed giant of our own neighborhood, wouldn't stand a chance. It would be engulfed, its massive atmosphere stripped and melted away by the sheer presence of this monster. The edge of UY Scuti would reach out over 2.3 billion kilometers, stretching all the way to the orbit of Saturn. The planet of the rings, which takes 29 years to complete a single orbit, would find its rings vaporized like morning mist as it skims the very surface of the star. This is the scale of nothingness. UY Scuti has a diameter of approximately 15 astronomical units, making it 1,700 times wider than our Sun. Its volume is so staggering that you could fit 5.1 billion suns inside it. To put that back into a relatable scale, if UY Scuti were the size of a football field, our Sun would be the size of a single ping pong ball. If you were to board a standard Boeing 777 at its normal cruising speed and try to fly a single circle around the circumference of this star, the trip would take you more than 1,200 years. Your great-great-great-grandchildren would still be mid-flight, and they would still have centuries of travel left before they saw the same point twice. Even light itself, the fastest thing in existence, struggles to navigate the scale of this giant. It takes about 14.5 seconds for a photon to circle our Sun. To circle UY Scuti, that same photon would need 7 hours. Think about that. In the time it takes for you to work a full day or sleep through the night, a beam of light has only managed to complete one single lap around this one individual star. This is physics at its absolute limit, a beast that is scraping the edge of the Hayashi limit, the theoretical maximum size a star can reach before its own internal gravity starts to lose the battle against its radiation pressure. But being a Titan comes with a terrifying cost. In the universe, the more massive and luminous you are, the faster you burn. While our modest Sun will live for 10 billion years, UY Scuti is already in its final act, despite being only 10 to 20 million years old. It is a star that has left the stability of the main sequence, the balancing act of hydrostatic equilibrium, and has entered a phase of violent, erratic existence. It is no longer just a star, it is an engine of instability, a pulsating variable that breathes and churns. Its outer layers are so loosely bound by its own gravity that they are millions of times less dense than the air we breathe. It is a star of smoke and glowing fog, barely holding itself together as it prepares for an end that will be as spectacular as its life. In a few million years, a mere blink in the eyes of the cosmos, UY Scuti's core will collapse. The resulting explosion won't be a simple supernova. It will be a hypernova, a blast with the power of 100 supernovas combined. It will release massive amounts of gamma radiation, obliterating anything that might have been orbiting it and outshining entire regions of our galaxy for a brief, brilliant moment. As we look at this faint orange dot in the Scutum constellation, we are forced to confront a profound truth. We live around an average star in a quiet corner of space, and that is the only reason we are here to wonder about giants at all. On our tiny 2mm peppercorn, atoms that were forged in the hearts of ancient supernovas long before UY Scuti even existed, learn to think, to wonder, and to measure the size of the monsters in the dark. UY Scuti will eventually fade, its light will vanish, and what remains will be a neutron star, or perhaps even a black hole, a tiny, ultra-dense ghost of something once colossal. But the story of this titan reminds us that the universe operates on a scale that we cannot comprehend, let alone exhaustively explore. We are just beginning to climb the cosmic beanstalk, and as we move closer to the edge of this giant, we must prepare to face a reality that is far stranger and more terrifying than we ever imagined. The journey to the largest star in the universe has only just begun. For over a century and a half, the greatest titan in our local universe hid in plain sight, disguised as nothing more than a serial number in a dusty catalogue. While humanity was busy with the Industrial Revolution, the rise and fall of empires, and the birth of the atomic age, UY Scuti was already there, a silent sentinel, 9,500 light-years away in the constellation Scutum. But to the astronomers of the 19th century, it wasn't a monster. It wasn't even a curiosity. It was just a point of light, one of millions, that seemed to serve no purpose other than to be counted and filed away. The story of this 150-year shadow begins in 1860 at the Bonn Observatory in Germany. This was the era of the Bonner Durchmusterung, one of the most ambitious star catalogues ever attempted at the time. These astronomers weren't looking for hypergiants or reality-breaking physics. They were simply trying to map the heavens piece by piece using the limited technology of their age. They looked through their telescopes and saw a faint reddish dot, hardly a blazing beacon of power, and assigned it a cold clinical name, BD125055. It was designated simply as the 5055th star, recorded between 12 and 13 degrees south of the celestial equator. For decades, that was the extent of our relationship with this giant. It was an entry in a ledger, a tiny spark in the Shield constellation, Scutum, which is Latin for shield. It sat there, buried deep within the Cygnus Rift, a region of the Milky Way so choked with dark bands of dust and gas that the star's true brilliance was effectively smothered from our perspective. This is the essence of the 150-year shadow. We possessed the data for its existence long before we possessed the imagination or the technology to understand what it actually was. While it sat in the archives as a boring numerical designation, it was actually a star so vast that 5 billion suns could fit within it. But because of its vast distance, somewhere between 5 to 10,000 light-years, and its relatively low temperature, UY Scuti is not visible to the naked eye. You would need powerful binoculars or a small telescope just to spot the very thing that, if placed in our solar system, would delete every planet from Mercury to Jupiter. The transition from a numbered dot to a cosmic enigma began when subsequent observations started to notice something strange about BD 125055. Its light wasn't constant, it flickered, it ebbed and flowed with a slow rhythmic instability. This discovery changed everything. Under the naming conventions of astronomy, where variable stars are named in the order of their discovery within a constellation, the star was reclassified. It became the 38th variable star discovered in the constellation Scutum, and thus it received the name that would eventually become legendary, UY Scuti. But even with its new name, the star remained a mystery, lurking in the background of more famous giants like Betelgeuse or Antares. For the better part of a century, we assumed we knew the limits of how large a star could grow. We believed in the Hayashi limit, a theoretical maximum size a star can reach before its own internal gravity starts to lose the battle against its radiation pressure. We believed that stars followed a predictable path on the Hertzsprung-Russell diagram, moving from a stable main sequence into a predictable death. UY Scuti, however, was quietly breaking those rules 9,500 years in the past, its light slowly travelling toward us through the interstellar medium. The reclassification into a red hypergiant wasn't just a change in title, it was a realization that we were looking at a titan on the brink. This is a classification reserved for the rarest and most extreme stars in the universe, stars that are so massive and luminous that they are in the process of literally destroying themselves. UY Scuti is a pulsating variable, but that word variable is doing a lot of heavy lifting. The star doesn't just flicker, it breathes. On a cycle of roughly 740 days, the entire star expands and contracts with the violence of 1,000 supernovas. This instability means its size isn't a fixed value. It's a moving target, which is why astronomers struggled for so long to pin down its true scale. It wasn't until the early 2010s that UY Scuti finally stepped out of the shadow and into the throne. In 2012, a team of astronomers using the Very Large Telescope in Chile re-estimated its size and distance. When they ran the numbers, the results were so staggering, they almost didn't seem real. 1,700 times the diameter of our Sun. It was the new king, surpassing giants like VY Canis Majoris. But as we've discussed, this throne is built on a measurement uncertainty theory. Because it is buried in the dust of the Cygnus Rift, measuring its exact distance, and therefore its exact size, is like trying to measure the height of a mountain through a thick blizzard. This is why the 150-year shadow still lingers. Even today, with the Gaia spacecraft suggesting it might be smaller and closer, the debate continues. Some argue that its enormous size might be an envelope illusion, a trick played by the diffuse gas clouds and stellar winds that surround it. Others look at its low mass compared to its size and whisper about stellar cannibalism, wondering if it reached this impossible radius by devouring smaller stars in its dense nursery. As we look back at those early German records from 1860, the irony is inescapable. The astronomers who first marked down BD 125055 thought they were recording a minor detail of the night sky. They had no way of knowing that their minor detail was a sun so large that light itself, the fastest thing in existence, would take 7 hours just to circle it once. They didn't know that this star was losing mass at such a staggering rate that it was seeding the surrounding space with heavy elements like oxygen, carbon and nitrogen, the very ingredients for future worlds. This is the legacy of the 150-year shadow. It serves as a humbling reminder that the universe is often far larger and more complex than our instruments can initially detect. UY Scuti was never just a number, it was a warning. It warned us that our models of stellar evolution were incomplete, and that the limits we placed on nature were merely reflections of our own limited perspective. The star had been waiting in the Scutum constellation for millions of years, burning through its fuel with a frantic, desperate intensity, just waiting for us to finally develop the technology to see it for what it truly was. A dying king on a throne of light-polluted fog. Now that the shadow has been lifted, the mystery has only deepened, for as we look closer, we realize that the largest star might be the greatest illusion of all. In the grand theatre of the cosmos, a crown is not made of gold or jewels. It is made of mathematics, light, and the fragile consensus of a species that has only recently learned how to measure the dark. For nearly a decade, UY Scuti wore that crown as the undisputed king of the stars, a celestial titan so vast it redefined the very word large. But in the universe of astrophysics, truth is a moving target. In 2018, a high-precision dagger was unsheathed by a spacecraft named Gaia, and it struck directly at the heart of the king's legacy. This is the story of the measurement war, a conflict that turned a cosmic god into a fallen noble and forced us to confront the fact that our maps of the universe are often written in pencil, waiting for a better eraser. To understand why UY Scuti's throne began to crumble, we first have to understand the measurement uncertainty theory. In our daily lives, if we want to know how big something is, we simply walk up to it with a ruler. But in deep space, there are no rulers. We are forced to infer the size of a star through a complex, three-legged stool of data: luminosity, temperature, and distance. If any one of those legs is even slightly off, the entire calculation collapses. UY Scuti is what we call a red hypergiant, a star in its final, most violent act of existence. Because it is so extreme, it doesn't have a solid surface. Instead, it has a diffuse, extended atmosphere that makes it incredibly difficult to determine where the star ends and space begins. This is the envelope illusion, a possibility that what we are measuring is not the star itself, but a massive, light-polluted cloud of gas and dust being blasted away by intense radiation. This problem is compounded by where UY Scuti chose to live. It sits 9,500 light-years away in the constellation Scutum, but more importantly, it is buried deep within the Cygnus Rift. Astronomers call this the zone of avoidance. It is a region of the celestial sphere where the thick, dark bands of interstellar dust and the overwhelming light of the galactic plane combine to create a cosmic fog. Trying to measure UY Scuti from Earth is like trying to determine the exact size of a lighthouse beacon through a thick midnight blizzard. For years, we relied on traditional luminosity measurements, calculating its size based on how bright it appeared and how hot we thought its surface was. In 2012, those calculations gave us the legendary figure 1,700 times the radius of our Sun. At that size, UY Scuti was the king, comfortably surpassing previous record holders like VY Canis Majoris. But then came 2018, and with it, the Gaia mission. Gaia is a European Space Agency spacecraft designed with one goal: to map the Milky Way with unprecedented precision. It doesn't rely on how bright a star looks. Instead, it uses a technique called parallax. Think of it like this. If you hold your thumb out at arm's length and close one eye, then switch to the other, your thumb appears to jump against the background. By measuring that tiny shift as the Earth moves from one side of the Sun to the other, Gaia can use trigonometry to calculate a star's distance with terrifying accuracy. It is a mathematical dagger that cuts through the uncertainty of luminosity. When Gaia turned its high-precision instruments toward UY Scuti, the result was a bombshell that sent shockwaves through the astronomical community. The data suggested that UY Scuti was not 9,500 light-years away, but significantly closer, perhaps only 5,000 light-years from Earth. In the world of stellar measurement, distance is everything. If the star is closer than we thought, it doesn't need to be as large to appear as bright as it does. Based on Gaia's new distance estimate, UY Scuti's radius was revised downward from a monstrous 1,700 solar radii to a mere 755 solar radii. Let that sink in for a moment. In a single afternoon of data processing, the undisputed king of the universe was cut in half. At 755 solar radii, UY Scuti is still a titan. It would still swallow Mars and reach deep into the asteroid belt, but it is no longer record-breaking. It isn't even in the top 5. It was overtaken by stars like Stephenson 2-18, an absolute monster estimated to be 2,150 times wider than the Sun, sitting 19,000 light-years away. Stephenson 2-18 doesn't just break the records, it breaks our models. It blows past the Hayashi limit, the theoretical point where a star becomes too large to remain stable, by over 40%. It is a star that genuinely shouldn't exist, sitting in the same patch of sky where UY Scuti once reigned. But the measurement war is far from over. There is a catch to Gaia's data that the top 10 videos often skip. Parallax measurements lose their reliability at extreme distances, and 5,000 to 9,000 light-years is pushing the very edge of what even Gaia can pin down with total confidence. Furthermore, UY Scuti is a pulsating variable star. It breathes on a roughly 740-day cycle, its outer layers swelling and shrinking in chaotic rhythms. Its brightness is constantly changing, and its massive mass loss, shedding the equivalent of an entire Earth every month, creates a lumpy, irregular cloud of ejected material around it. This pulsation chaos means that the star's size isn't a fixed value, it's a moving target. Some astronomers argue that Gaia's sensors might have been tricked by the star's instability or by the thick dust of the Cygnus Rift. This creates a fascinating scientific drama. On one side, you have the traditionalists who point to UY Scuti's extreme luminosity and temperature as evidence of its 1,700 solar radii status. On the other side, you have the new guard, armed with Gaia's parallax data, arguing that the star is a fallen noble, a smaller, closer, but still impressive hypergiant that has been riding on a 150-year wave of measurement error. The astronomical community has not fully settled on the new figure. The debate remains an open wound in our understanding of the Milky Way's most extreme residents. Is UY Scuti the king, or is it a beautiful illusion? The truth is, we may never know for certain. The vast majority of stars are so immensely distant that we are essentially looking at them through a keyhole. Our sample size of 400 billion stars in the Milky Way is still a tiny fraction of the hundreds of sextillions of stars in the observable universe. Every time we sharpen our instruments, every time we launch a new probe like Gaia, the leaderboard changes. We found Stephenson 2-18, partially obscured, buried inside a crowded star cluster, and we almost missed it entirely. Who is to say that tomorrow we won't find a star even larger, hidden behind another band of dust? This measurement war reminds us of our own humility. We are a species that lives around an average star in a quiet corner of the galaxy, yet we have the audacity to try and measure the girth of a titan 9,500 light-years away. Whether UY Scuti is 1,700 times the size of the Sun, or only 755, it remains a testament to the sheer scale of cosmic possibility. It is a star that has lived fast and will die young, burning through its fuel with a frantic intensity while we argue over the numbers. Whether it sits on the throne or stands in the shadows of new giants, like Stephenson 2-18, UY Scuti's legacy is secure as the star that forced us to look deeper, to question our rulers, and to realize that in the kingdom of the giants, nothing is ever as solid as it seems. We're just beginning to climb the cosmic beanstalk, and as we look up at that faint orange dot in the Scutum constellation, we must accept that the king might be a ghost. But he is a ghost that still has the power to redefine our entire universe. Imagine our hypothetical starship, a vessel built to withstand the impossible, as it finally draws near the most formidable entity in the Scutum constellation. For weeks of travel, the view through the observation deck has been dominated by a wall of deep, somber red light that seems to consume the very stars around it. We have crossed 9,500 light-years of void, leaving our modest yellow-white sun behind until it became nothing more than a fading spark swallowed by the dark. Ahead of us lies UY Scuti, a titan so impossibly large that it stretches the very limits of what a star can be. From a distance, it appears as we expect a star to look, a majestic, roiling sphere of plasma. We prepare for the moment of contact, the moment our ship's sensors indicate we've reached the photosphere, that definitive surface where the energy balance of nuclear fusion meets the void of space. We brace for a violent impact, a sudden wall of fire that would swallow our inner solar system for breakfast. But as we cross the threshold that would normally be the orbit of Jupiter, something unsettling happens. There is no impact. Our instruments tell us we are now inside the largest star in the universe, yet the transition is almost imperceptible. This is the beginning of the envelope illusion, a paradox that suggests what we perceive from Earth as a solid, definitive boundary is actually a haunting cosmic trick. Most competitors show you a star with a hard, glowing edge, but they are ignoring the reality that UY Scuti has no true surface. As we enter the outer layers of this titan, we realize we are not flying through a liquid or a solid, but through a glowing fog. The material surrounding us is so incredibly diffuse that it is millions of times less dense than the very air you're breathing right now on Earth. This is the scale of nothingness manifest. We find ourselves drifting through 1.5 billion kilometers of superheated plasma, a journey so vast that if we were in a standard Boeing 777 at its normal cruising speed, it would take us over 1,200 years just to complete one lap around this nothingness. Yet inside this fog, the nothingness is the most terrifying part. You look out the window, and despite being deep within a hypergiant, you can still see the distant pinpricks of the Milky Way stars through the thin, hazy veil of the star's atmosphere. It is less like being inside a sun, and more like being trapped in a light-polluted cloud of gas and dust that is barely held together by a gravity that is losing its grip. As we push deeper into this 1.5 billion kilometer expanse, the physics becomes increasingly extreme. We are moving through a region where UY Scuti is literally tearing itself apart in slow motion. This isn't a stable kingdom. It is a war zone of pulsation chaos. The star is breathing, expanding and contracting on a roughly 740-day cycle, its outer layers swelling and shrinking with a violence that defies our best models. We feel the ship buffeted not by wind as we know it, but by stellar winds blasting outward at thousands of kilometers per second. The star is hemorrhaging mass, throwing away the equivalent of an entire Jupiter in single explosive burps. These eruptions create a surrounding nebula 10,000 astronomical units in length, a vast graveyard of gas that stretches 300 times the distance from our Sun to Neptune. The envelope illusion theory forces us to ask a chilling question: where does the star actually end? Because the radiation pressure from the core is so intense, it is constantly pushing the star's outer layers into the void, creating an extended atmosphere so vast it confuses our measurements from Earth. For thousands of kilometers, we travel through a superheated mist of oxygen, carbon, and nitrogen, the very ingredients for future life, being forged in a furnace that is currently in its final act. We are witnessing the aftermath of a star that has run out of hydrogen and is now desperately fusing heavier elements to stave off a core collapse. Every intuition we have about a star's edge is broken here. In our own solar system, the Sun has a clear dominant presence, but inside UY Scuti, the scale is so absurd that the word star starts to feel insufficient. We are inside a cosmic catastrophe happening in slow motion. The density is so low that the star is essentially a massive glowing vacuum. If you took a piece of UY Scuti's outer layer and brought it to Earth, it would be a better vacuum than most we can create in a laboratory. And yet, despite being made of almost nothing, this ghost is radiant. It shines with the energy of 400,000 suns combined, a somber red glow that permeates every inch of the 1.5 billion kilometers we are traversing. We are flying through the ashes of a dying king, a titan that is spending its last few million years of life seeding the universe with stardust. The realization sets in that UY Scuti is not a solid object we can land on, but a beautiful, terrifying illusion of scale. It is a star of smoke, a sun of fog, and a reminder that in a universe of billions of galaxies, the largest things we can find are often the most fragile. As we continue our journey deeper toward the core, the fog begins to thicken, and the nothingness starts to give way to the violent, crushing reality of a star that is preparing to end its life in the most powerful explosion the galaxy has ever seen. As we descend deeper into the glowing fog of UY Scuti's outer layers, we are forced to confront a mathematical nightmare that challenges everything we thought we knew about how stars are born. In the standard story of the cosmos, mass is destiny. If you want to be a giant, you have to be heavy. Our Sun is a modest, stable ball of gas, precisely because it has a modest amount of mass. If you look at stars like R13601, the most massive star ever found, the numbers make sense. It is 265 times the mass of our Sun, and its radius is 40 times larger. It is a dense, heavy powerhouse. But as we drift through the diffuse red haze of UY Scuti, we find a star that is essentially a cosmic contradiction. While it is 1,700 times wider than our Sun, large enough to fit 5.1 billion suns inside its volume, its mass is estimated to be a mere 7 to 10 times that of the Sun. This is the central mystery of the Cannibal King. Astronomers call it an impossible balloon. According to the laws of physics, a star with that little mass should not have enough gravitational glue to hold onto an atmosphere that stretches out to the orbit of Saturn. There is a theoretical line on the maps of the universe called the Hayashi limit. It is the maximum size a star can reach given its mass. If a star tries to grow larger than this limit, gravity is supposed to win the tug of war, pulling the material back in and forcing the star to shrink. UY Scuti isn't just touching that line, it is scraping the very edge of what is physically possible. It is a star that has inflated itself to a record-breaking radius while remaining incredibly light and empty. To find out how a star can cheat the grading system of the universe, we have to look back at its birth. UY Scuti didn't grow up in a quiet, isolated corner of the galaxy like our Sun. It lives in the Scutum constellation, a region incredibly rich with massive stars and dense stellar nurseries. In these crowded environments, the birth of a star is not a peaceful event, it is a violent, competitive scramble for resources. The stellar cannibalism theory posits that UY Scuti achieved its monstrous scale not through the slow, steady evolution of a single star, but through a dark and ancient feast. We have seen evidence of this kind of cosmic cheating elsewhere in the galaxy. When two massive stars collide and merge, the result is a true behemoth, an object far larger than anything possible through the normal devouring of an accretion disk. Some theorists believe that in the high-pressure environment of its nursery, UY Scuti may have absorbed nearby stellar material, or even swallowed smaller companion stars during its early, volatile years. It may have started as a more modest star that effectively cannibalized its siblings, stripping their mass to fuel an unnatural growth spurt that allowed it to balloon outward into the Titan we see today. This origin story adds a layer of narrative tension to the star's existence. It isn't just a giant, it is a scavenger, a Frankenstein's monster of the Scutum constellation built from the remains of other stars. This would explain why its mass is so low compared to its volume. It didn't have the internal core pressure to grow this large naturally, so it cheated the Hertzsprung-Russell diagram by taking on external material that it can now barely hold on to. This is why the star is so unstable, why it pulses and churns with such violence. It is a star of smoke and glowing fog, an object that is more than 99% empty space in its outer layers. But being a cannibal king comes with a staggering price. In the universe, the more you feast, the faster you die. While a stable star like our Sun will live for 10 billion years, UY Scuti is already in its final act despite being only 10 to 20 million years old. It has burned through its fuel with a frantic, desperate intensity that reflects its violent origins. Because it is so diffuse and its gravity is so weak at the edges, it is constantly hemorrhaging its own lifeblood into the void. It throws off the mass of an entire Jupiter in single explosive burps, creating a surrounding nebula 10,000 astronomical units in length. It is a star that is literally tearing itself apart, unable to sustain the massive, hollow kingdom it built for itself. As we navigate this 1.5 billion kilometre expanse of superheated plasma, we realise that UY Scuti is a warning about the limits of growth. It is a star that grew too big, too fast, and by the wrong means. It sits on a throne of light-polluted fog, a titan on the brink that could collapse into a black hole, or explode as a hypernova at any moment. Every atom of heavy elements it currently possesses, the oxygen, carbon and nitrogen it is currently burping into space, was forged in the desperate heat of a star that shouldn't exist. We are looking at a ghost story written in mass and volume, a reminder that in the grand scheme of the cosmos, even the most legendary kings are often just victims of their own impossible scale. To understand the violent instability of UY Scuti, you must first understand that every star you see in the night sky is not a peaceful object, but a site of a continuous, multi-billion-year war. In the world of astrophysics, we call this the state of hydrostatic equilibrium, but that clinical term hides a much more brutal reality. Imagine an almost incomprehensible amount of matter, billions of times the volume of our Sun, being crushed inward by its own gravity with a force that wants to collapse the entire star into a single point. At the same time, deep in the core, the star is fighting back. Atoms are being slammed together so hard their nuclei break apart and fuse, releasing a violent burst of energy that pushes outward with the power of millions of hydrogen bombs. This tug of war, gravity pulling in and nuclear fusion pushing out, is the only reason a star exists at all. For a star like our Sun, this war is a stalemate that has lasted for 5 billion years. But as we approach UY Scuti, we are witnessing a star where the peace has been shattered and the war has turned into a chaotic, rhythmic slaughter. UY Scuti has left the stable main sequence phase of its life. It has exhausted the hydrogen in its core, and without that constant outward pressure, gravity briefly won the battle, causing the core to start collapsing. But in a universe of extreme physics, collapse often leads to a terrifying resurgence. As the core shrank, it heated up to temperatures that the star had never experienced before, reaching a point where it began to fuse helium into even heavier elements. This intense heat didn't just stay in the core, it bled out into the outer shells, causing hydrogen atoms in the surrounding layers to ignite. This sudden massive surge of outward energy was so powerful that it overwhelmed the star's gravity, forcing the outer layers to swell outward with a violence that turned a modest star into a red hypergiant. This is the engine of the giant, a core that is burning hot and fast and a body that has inflated to the point of structural failure. This brings us to the most unsettling feature of UY Scuti, a phenomenon we have identified as pulsation chaos. Because the star is so vast and its outer layers are so diffuse, its gravity has become weak and thin, unable to maintain a constant grip on its own atmosphere. UY Scuti is not a static object, it is a pulsating variable star that is quite literally breathing in the void. On a cycle that lasts roughly 740 days, the entire star expands and contracts in a rhythmic, chaotic struggle for survival. It is as if the star is gasping for air, its photosphere swelling outward for hundreds of millions of kilometers before the inward pull of gravity momentarily regains control and drags the material back down. This 740-day breath is not the gentle movement of a planet. It is a cosmic catastrophe occurring in slow motion. During these pulsations, the star's size is not a fixed value, but a moving target that defies our best mathematical models. When the star exhales, its radius pushes out toward the orbit of Saturn, and when it inhales, it may shrink significantly, leading to the massive measurement uncertainties that have plagued astronomers for 150 years. This instability is so extreme that the star has essentially become a titan on the brink, an object that is tearing itself apart simply by existing. The consequence of this breathing is a phenomenon called mass loss, and in the case of UY Scuti, the scale of this loss is staggering. Every time the star pulses, its outer layers become less tightly bound by gravity, allowing stellar winds to blast material outward at speeds of up to 3,000 kilometers per second. UY Scuti is capable of burping out the mass of an entire Jupiter in a single explosive event. Imagine the Sun casually throwing away an entire planet every month. That is the daily reality of this hypergiant. These violent burps are filled with heavy elements that the star has forged in its desperate core: oxygen, carbon, and nitrogen, the very building blocks of life being scattered into the dark in a frantic, final act of desperation. This ejected material doesn't just vanish, it forms a chaotic, lumpy, and irregular cloud of gas and dust that surrounds the star like a shroud. Astronomers have observed these swirling expulsions, creating a nebula that stretches 10,000 astronomical units in length, 300 times the distance from our Sun to Neptune. This is the envelope illusion made manifest. From Earth, we see a giant star, but we are also seeing the ghost of the star, the massive, light-polluted cloud of its own shed skin that obscures the true boundary between the photosphere and the void. This shroud is so thick and lumpy that it creates a feedback loop of instability. The more mass the star loses, the less gravity it has to hold onto its remaining layers, allowing them to expand even further, which in turn leads to even more mass loss. It is a star caught in a terminal downward spiral. As we navigate our ship through this 1.5 billion kilometre expanse of pulsation chaos, the existential horror of the scale begins to set in. We are travelling through a region of space where a single object is breathing with the power of 400,000 suns. The surface we are trying to land on is actually a roiling, churning sea of plasma that could expand by millions of kilometres while we are in mid-flight. For any hypothetical planet that might exist in this system, there is no such thing as a stable climate or a predictable orbit. The star's pulsations would create a shifting habitable zone that would swallow worlds whole and then spit them back out as vaporized dust. Why has the universe allowed such a monster to exist? The sources suggest that UY Scuti is a perfect cosmic accident. It is a star that started with an immense amount of mass, perhaps 20 to 30 times that of our Sun, and lived a fast, violent life that burned through its fuel in a mere 10 million years. It is currently in a short advanced phase of life that comes just before the ultimate collapse. In its final few million years, it has become a titan of nothingness, a star that is 10 billion times the volume of the Sun, but so diffuse and empty that it is more like a glowing fog than a solid sphere. The hydrostatic equilibrium war that defines the life of every star is reaching its conclusion here. The outward pressure of fusion is no longer a steady stream, but a series of desperate explosions, and the inward pull of gravity is no longer a firm grip but a failing embrace. UY Scuti is a star that is living on borrowed time. Its 740-day rhythm, a countdown to a hypernova explosion that will be one of the most powerful events in the history of the galaxy. We are looking at a sun that has broken the grading system of the universe, a cannibal king that feasted on its siblings only to find that its own body has become too large for its soul to inhabit. As we pull back from the roiling, pulsating edge of this giant, we are left with a sobering realization. The very chaos we are witnessing, the shedding of mass, the violent pulsations, the breathing of the star, is the only reason we exist. Every atom in your body heavier than helium was once caught in a tug of war exactly like this one. We are the survivors of a stellar war, the ashes of dead giants that once defied the limits of the dark. UY Scuti is currently seeding the universe with the ingredients for the next generation of life, even as it prepares to vanish into a black hole or a neutron star. The king is dying, and his final breath is a gift of dust to the cosmos. To find a place where life could even begin to contemplate the existence of UY Scuti, we have to leave the glowing fog of its outer atmosphere far behind and travel into the true deep of the Scutum constellation. We are moving away from the star, pushing our ship out past the equivalent orbits of Saturn, Uranus, and Neptune into a cold, dark void that would make our own Kuiper Belt look crowded. We have to travel 1.5 trillion kilometers, approximately 1,000 astronomical units, away from the star's center before the heat and radiation drop to a level that wouldn't instantly vaporize organic matter. This is the forbidden habitable zone. It is a lonely, isolated shoreline on the edge of a cosmic ocean, and it is the only place in this entire system where the word home could ever be uttered. As we approach a hypothetical planet on this distant frontier, the first thing you notice is the light. Because we are so far away, the physics of time and space start to behave in ways that defy our human intuition. Even light, the fastest thing in the universe, takes a full month to travel from the surface of UY Scuti to this world. If the star were to suddenly vanish, the inhabitants of this planet wouldn't know for 30 days. They are living in the star's past, bathed in the somber red glow of a giant that is always a month older than it appears to be. The star doesn't look like our sun. It is a massive, bloated, deep crimson disk that dominates the sky, casting long, bloody shadows across a frozen landscape of nitrogen ice and jagged obsidian mountains. On this world, the very concept of time is broken. Because the planet must maintain such a massive distance to stay in the Goldilocks zone of a hypergiant, its orbit is agonizingly slow. One single trip around UY Scuti, 1 calendar year, takes 10,000 Earth years. Think about the scale of that history. To a civilization born here, the entirety of recorded human history, from the first clay tablets in Sumer to the launch of the James Webb Space Telescope, would represent just a single year of their lives. If this world has seasons like Earth, tilted on its axis, each season would last for 2,500 years. Imagine being born in the middle of a 2,500-year summer. To you, the idea of winter would be nothing more than a myth, a legendary tale told by ancestors who lived and died 20 generations ago. You would spend your entire life under a constant, unchanging red sky, believing that the climate of your world was a static, eternal truth. Entire civilizations would rise, build empires, develop languages, and crumble into dust without ever experiencing a change in the weather. For these people, what we call seasons wouldn't be perceived as a cycle at all. Instead, they would see them as natural, millennia-long climate changes, shifts in the very fabric of the world that occur over vast, generational spans of time. They would be a species that thinks in centuries, where a decade is a mere heartbeat, and a century is just a weekend. But this is why we call it the forbidden habitable zone. This world is a beautiful lie. While the distance might suggest a cold, peaceful stability, the reality of living next to a red hypergiant is a waking nightmare. This is the great twist that the standard documentaries ignore. The star's pulsation chaos makes long-term life an impossibility. UY Scuti is not a stable sun. It is a violent engine of mass loss. Even at a distance of 1.5 trillion kilometers, this planet is not safe. The star is constantly undergoing what astronomers call violent burps. Because UY Scuti is so loosely held together by its own gravity, its internal radiation pressure is constantly winning the war. Every few years, the star experiences an explosive eruption of mass, ejecting the equivalent of an entire Jupiter into space in a single chaotic event. These aren't just solar flares, they are massive, lumpy clouds of superheated plasma and heavy elements, oxygen, carbon, and nitrogen, blasting outward at thousands of kilometers per second. These Jupiter-sized burps create a surrounding nebula 10,000 astronomical units in length, a graveyard of gas that acts like a cosmic shotgun blast aimed at anything in its path. When one of these mass ejection events reaches our hypothetical planet, it doesn't matter how far away we are. The stellar wind isn't a breeze, it's a relentless storm of high-energy particles that would strip away a planet's atmosphere layer by layer, turning a potentially habitable world into a bare, radiation-scorched core in a matter of centuries. The habitable zone itself is a moving target. Because UY Scuti pulses on a 740-day cycle, its luminosity and temperature are constantly shifting. The Goldilocks zone is not a stable ring, it's a vibrating, unpredictable front. A world that is in the just right temperature today might find itself in a deep freeze tomorrow, or worse, engulfed by a sudden expansion of the star's diffuse outer layers. And lurking behind all of this is the ultimate countdown. UY Scuti is a titan on the brink, a star that has already reached the final stages of its life. It is 10 to 20 million years old, and in the eyes of the cosmos, it is already dead. Within the next million years, a mere blink in the 10,000-year orbit of our hypothetical world, the star will reach the end of its fusion chain. When it reaches iron, the engine will stop. Gravity will win in less than a second and the core will collapse. The resulting hypernova won't just be an explosion, it will be an act of cosmic erasure. It will detonate with the power of 100 supernovas, releasing massive amounts of gamma radiation that would obliterate any planetary system, regardless of how far back in the forbidden zone it tried to hide. For the inhabitants of our 10,000-year orbit world, there would be no warning. The light of their own sun's death would reach them at the same time as the radiation, vaporizing their atmosphere, their oceans, and their 2,500-year-long history before they even realized the red disk in the sky had changed. This is the dark irony of UY Scuti, the very thing that makes it so fascinating. Its impossible scale and its violent, life-seeding instability is the very thing that ensures no life can ever truly call it home. It is a star that demands to be watched from a distance, a ghost story that we are lucky to observe from the safety of our 9,500 light-year vantage point. We are made of the stardust that stars like this ejected eons ago, the ashes of dead giants that eventually learned to think and wonder, But to return to a giant like UY Scuti is to realize that the cradle of the universe is also its most dangerous furnace. We are the survivors of a stellar war, living around a modest, stable sun that has given us the one thing UY Scuti can never provide: time. As we look back one last time at the crimson world on the edge of the abyss, we realize that the forbidden habitable zone isn't a place for life to thrive. It's a front row seat to the most spectacular and lethal show in the galaxy. The king is dying, and he will take everything he ever created with him. In the quiet, stable neighborhood of our own solar system, we've come to view the sun as a symbol of permanence. For 5 billion years, it has held onto its mass with a jealous grip, losing only a tiny fraction of its substance to the solar winds that dance across our planets. But as we journey deeper into the Scutum constellation, we encounter a star that has abandoned the very idea of stability. UY Scuti is not just a giant, it is a tragedy in motion, a celestial titan that is currently hemorrhaging its own body into the void at a rate that defies every law of stellar conservation. While you are told this star is the largest in the universe, the secret your competitors missed is that UY Scuti is actively tearing itself apart before it even has the chance to die. To understand this great weight loss, we have to look at the war being waged inside the star's diffuse 1.5 billion kilometer body. For millions of years, UY Scuti maintained a state of hydrostatic equilibrium, a perfect balance where the inward crush of gravity was matched by the outward blast of nuclear fusion. But that balance is now a memory. Because UY Scuti has ballooned to such an impossible size, 1,700 times the radius of the Sun, its outer layers have become incredibly thin, millions of times less dense than the air you're breathing right now. At these extreme distances from the core, the star's gravity is weak and leaky, losing its ability to hold on to the very plasma that gives the star its form. This is where the mechanism of destruction takes over. Deep within the core, the radiation pressure is so intense that it doesn't just push against gravity, it overpowers it. This energy acts like a cosmic hammer, smashing into the outer layers and blasting them away into space. But the most fascinating and obscure part of this process is the role of dust. In the relatively cool outer layers of UY Scuti, which are 40% cooler than our Sun, heavy elements like carbon and oxygen begin to condense into solid grains. This dust acts like a sail. The star's intense radiation hits these dust grains and pushes them outward, and as the dust flies away, it drags the surrounding gas along with it. This creates powerful stellar winds that are not mere breezes but relentless, supersonic storms. Our ship's sensors would detect these winds screaming away from the star at speeds of up to 3,000 kilometers per second. At that speed, you could travel from the Earth to the Moon in just over 2 minutes. This is the mechanism of the hemorrhage, a constant, violent stripping of the star's skin by its own internal light. UY Scuti is not just losing mass, it is undergoing what astronomers call violent burps. In a single one of these explosive events, this hypergiant can blow off the mass of an entire Jupiter. Imagine the Sun casually throwing away the largest planet in our solar system as if it were a speck of dust. That is the scale of the mass loss occurring every few years in the Scutum constellation. This creates a terrifying feedback loop that the standard documentaries never mention. As UY Scuti loses mass, its total gravitational grip becomes even weaker. With less gravity to hold it back, the star's outer layers expand even further into the void. This expansion makes the layers even more diffuse and easier for radiation to blast away, which leads to even more mass loss. The star is caught in a terminal downward spiral, a titan on the brink that is literally expanding itself into non-existence. It is a star that is too big for its own good, a cannibal king that feasted on its siblings only to find that it can no longer support the weight of its own kingdom. The result of this 10 million year long hemorrhage is the creation of a shroud, a vast, lumpy, and irregular nebula of ejected material that surrounds the star. This cloud of gas and dust stretches for 10,000 astronomical units, a distance 300 times greater than the gap between our Sun and Neptune. From a distance, this nebula creates the envelope illusion, obscuring the true boundary of the star and making it look even larger and more mysterious than it already is. We are not just looking at a star, we are looking at a star that is drowning in its own shed skin, a sun that is being smothered by the very atoms it worked for millions of years to forge. This is why UY Scuti is tearing itself apart before it even reaches the end of its fusion chain. It is losing the battle of scales. It has 10 billion times the volume of our Sun, but only about 7 to 10 times its mass, meaning it is essentially a glowing fog, a sun made of almost nothing. This low density is the star's fatal flaw. It is a perfect cosmic accident, a star that managed to inflate to the size of Saturn's orbit, while having the structural integrity of smoke. As we fly our hypothetical ship through these screaming stellar winds, we realize that the great weight loss is not a transition, it is a death rattle. But there is a strange, haunting beauty to this destruction. The material UY Scuti is throwing away, the mass of Jupiters and the dust of heavy elements is not being wasted. These swirling expulsions are the seeds of the future. The oxygen you breathe and the carbon in your cells were likely forged in a hemorrhage, just like this one, millions or billions of years ago. UY Scuti is a dying king, but his final act is one of ultimate generosity. By tearing himself apart, he is enriching the interstellar medium, creating the stellar nurseries where the next generation of stars and planets will be born. The star's time is running out. Within the next few 100,000 years, a mere blink in the eyes of the cosmos, the hemorrhage will reach its conclusion. The core will eventually produce iron, the one element it cannot fuse, and the outward pressure will vanish in an instant. But long before that happens, UY Scuti will have already given most of itself back to the universe. It is a star that refuses to go quietly into the night, choosing instead to blast its legacy across the Scutum constellation in a 10,000 astronomical unit long trail of stardust. We are witnessing the aftermath of a titan, a ghost story written in mass loss, reminding us that even the largest things in the universe must eventually surrender to the void. In the grand, violent history of the cosmos, there is no such thing as a peaceful end for a titan. We have spent our journey marvelling at the scale of UY Scuti, peering through its glowing fog, and tracing the cannibalistic hunger of its youth. But now we must face the reality that every second we watch this star, we are watching a countdown. UY Scuti is currently in its final act, a period astronomers call the pre-supernova hypergiant collapse phase. In the eyes of the universe, this star is already a ghost. While our modest sun has the luxury of a 10 billion year lifespan, UY Scuti has burned through its entire existence in a frantic, desperate burst of 10 to 20 million years. It is an old soul trapped in a relatively young body, and the engine that has kept it inflated to such impossible proportions is finally running out of tricks. To understand the tragedy of the hypernova countdown, you have to understand the dead end of physics that occurs in the star's core. For millions of years, UY Scuti has stayed alive through a process of substitution. When it ran out of hydrogen, it didn't die. It simply turned up the heat and began fusing helium. When the helium runs dry, it will move to carbon, then neon, then oxygen, and then silicon. With each new element, the stakes get higher and the time remaining gets shorter. While hydrogen fusion can last for millions of years, the final stages of silicon fusion into iron might last for only a few days or even hours. This is where UY Scuti hits a wall that no amount of mass or volume can overcome. Iron is the death sentence of stars. In the heart of the core, when silicon fuses into iron, the reaction suddenly stops producing energy. Fusing iron actually consumes energy rather than releasing it. In that precise moment, the outward radiation pressure, the only thing that had kept this 5 billion sun-sized balloon from popping for 20 million years, simply vanishes. The hydrostatic equilibrium that we've discussed throughout this journey is finally irrevocably broken. What happens next is a phenomenon that defies human language. This is the pre-supernova hypergiant collapse. Without the outward push of fusion, gravity, the silent predator that had been waiting since the star's birth, wins the war in less than a single second. The core, an object once the size of Earth, collapses into a space no larger than a city, becoming a neutron star or a black hole. But the star's outer layers, that 1.5 billion kilometre expanse of glowing fog, haven't received the news yet. They begin to fall inward, chasing the collapsing core at a significant fraction of the speed of light. When that falling mountain of plasma hits the ultra-dense core, it bounces. This rebound creates a shockwave so powerful, it tears the star apart from the inside out. But UY Scuti faces a choice that smaller stars never have to make, a cosmic fork in the road that astronomers are still debating in the pre-supernova hypergiant collapse theory. The first option is the hypernova, a name that is almost too small for the event it describes. Because of UY Scuti's extreme scale and remaining mass, it wouldn't just be a supernova, it would be an explosion over 100 times more powerful than a standard stellar death. It would release massive amounts of gamma radiation, outshining entire regions of the Milky Way and signalling its end to the rest of the galaxy in a brilliant, violent flash that would be visible on Earth even in broad daylight. However, there is a second darker possibility lurking in the law vault, the direct collapse or the failed supernova. Some theorists argue that UY Scuti has lost so much of its outer shell through its great weight loss and pulsation chaos that it might skip the explosion entirely. Instead of a spectacular flash, the star might simply wink out. In this scenario, the core collapses so rapidly and with such overwhelming mass that it drags the entire star down with it, swallowing its own light before the explosion can even begin. the king of stars wouldn't go out with a bang, but with a silent, terrifying descent into a black hole, leaving nothing behind but an empty patch of sky where a Titan once stood. Whether it chooses the scream of a hypernova or the silence of a black hole, there is an eerie realization that we must confront as we watch UY Scuti from our telescopes today. This is the time lag paradox. UY Scuti is 9,500 light years away from us. That means every photon of light we see, every flicker of its variable brightness, and every violent burp we record actually happened nearly 10,000 years ago. When that light left Scutum, human beings were just beginning to settle into the first agricultural villages. Because red hypergiants have such extremely short lifespans, and UY Scuti is already showing every symptom of a star in terminal decline, the math suggests a haunting conclusion. The death signal might already be on its way. It is entirely possible that UY Scuti has already collapsed. It might have already exploded as a hypernova, and that wall of gamma radiation and blinding light is currently racing through the 9,500 light-years of void toward our solar system at the speed of light. We are looking at a ghost story written in the stars, a sun that may have vanished millennia ago, but whose ghost still dominates our telescopes because the news of its death simply hasn't reached us yet. Imagine the moment that signal finally arrives. For 9,500 years, the message has been travelling through the Cygnus Rift, passing through the dark bands of dust and gas, crossing the vast emptiness between the spiral arms of our galaxy. When it hits Earth, the faint orange dot in the constellation Scutum will suddenly ignite, becoming a second sun in our sky, a spectacle of light that reminds us that we are just small observers in a universe of giants. But until that moment, we wait in the shadow of the countdown. We watch a star that is essentially a cosmic accident, a Titan on the brink, that is currently fusing the very iron that'll kill it. We are witnessing the final frantic breaths of a king. Whether UY Scuti ends as a hypernova that seeds the universe with the ingredients for new life, or as a black hole that devours its own legacy, its fate is already sealed by the laws of physics. The clock is ticking, the iron is forming, and somewhere in the 9,500 light-years of darkness between here and Scutum, the light of the universe's greatest explosion may already be heading straight for us. We have spent our journey travelling across 9,500 light-years of void, peering through a glowing fog of superheated plasma and witnessing a star that is essentially tearing itself apart in slow motion. We have measured the impossible scales of UY Scuti and its rivals, debating numbers and parallax data as if we were accountants of the infinite. But now, as we stand on the edge of this Titan's final collapse, we must confront a question that science alone cannot answer. Why do we care? Why does a species living on a tiny 2mm peppercorn of a planet feel such a profound existential pull toward a dying giant that would vaporize us in a heartbeat? Why do we spend our short lives building telescopes and launch vehicles to look at a monster that is 9,500 years in our past? The answer lies in a shift of perspective, a realization that Scuti is not just a distant object to be measured, but a cosmic mirror. To look at this star is to look at our own prehistory. Throughout this documentary, we have framed UY Scuti as a terrifying beast, a cannibalistic king and a ghost of the Scutum constellation. But as we reach the end of its story, the narrative undergoes a fundamental transformation. We move from the science of the large to the philosophy of the connected. We realize that the terrifying scale of UY Scuti is not an obstacle to our understanding. It is the very reason we are here to understand it in the first place. This is the Stardust legacy. To understand our connection to this dying giant, we have to look inside the furnace. Throughout its violent life, UY Scuti has been doing more than just expanding and pulsing. It has been practicing the art of cosmic alchemy. For millions of years, its core has been a pressure cooker, slamming atoms together with such ferocity that it has rewritten the periodic table. It started with hydrogen, the simplest and most abundant element in the universe. But as the star aged and moved off the main sequence, it began to fuse helium, then carbon, then neon, then oxygen, and finally silicon. Every step of this fusion chain represents a new level of complexity being birthed from the chaos. And here is the bridge between the hypergiant and the human. Every single atom in your body that is heavier than helium was forged in a furnace exactly like this one. There is no other way for these elements to exist in the universe. The carbon that forms the basis of your DNA, the oxygen that you are breathing right now as you listen to these words, the nitrogen that makes up the majority of our atmosphere, and the iron that carries oxygen through your veins. All of it was once trapped inside the roiling, superheated heart of a dying star. UY Scuti is not just a distant light, it is a manufacturing plant for the ingredients of life. We are not just observers of the cosmos, we are the walking, talking, thinking remnants of dead giants. This is the profound irony of stellar evolution. Stars must die so that the elements of life can emerge. If stars like UY Scuti were stable and lived for trillions of years like red dwarfs, the universe would be a cold, simple place made of nothing but hydrogen and helium. There would be no rocky planets, no oceans, no carbon-based organisms, and no consciousness to marvel at the night sky. The very instability that makes UY Scuti so terrifying, the pulsation chaos, the great weight loss, and the violent burps is the mechanism that seeds the galaxy. When UY Scuti sheds the mass of an entire Jupiter every few decades, it is not losing its body, it is investing it in the future. It is scattering the seeds of oxygen and carbon across 10,000 astronomical units of space, enriching the interstellar medium with the heavy elements needed to build the next generation of worlds. Think about the iron in your blood for a moment. That iron is a direct result of the very same hypernova countdown we discussed. Iron is the final element a star can produce before it collapses. It is the signature of a star that has reached its limit. When UY Scuti finally explodes or collapses into a black hole, it will release a shockwave that blasts these heavy elements out into the dark. We are literally the ashes of dead stars. As Carl Sagan famously noted, we are made of stardust. We are the way the universe has found to know itself. When we point our telescopes at the Scutum constellation, we are not just looking at a star. We are a collection of ancient stellar atoms looking back at their own birthplace. The final image of our journey is one of both ending and beginning. We watch as the glowing fog of UY Scuti finally begins to fade. The King of the Stars has reached the end of his reign. Whether he vanishes into the silent embrace of a black hole, or detonates in a hypernova that outshines the Milky Way, the result is the same. The Titan is gone. But in its place, a new story begins. The ejected guts of the star, those vast lumpy clouds of gas and dust, do not simply drift away into nothingness. They become stellar nurseries. In the millions of years following the star's death, gravity will begin to work on those remnants. The clouds of carbon, oxygen, and iron will start to clump together, drawn in by their own mutual attraction. These nurseries will become the birthplaces of new, smaller, and more stable stars. Stars like our Sun. Around these new suns, the heavy elements will settle into disks, cooling and colliding until they form rocky planets. And on one of those planets, billions of years from now, the cycle may repeat. Water may flow in oceans made of oxygen and hydrogen, forged in UY Scuti's final breaths. Life may emerge, built from the carbon discarded by a dying king. We care about UY Scuti because its story is our story. Its violent existence provided the raw materials for our quiet corner of the galaxy. We live on a tiny planet around an average star because giants like UY Scuti lived fast and died hard billions of years ago. The philosophical shift is this: we do not look at the largest star to feel small, we look at it to find our scale. We look at it to remember that we are part of a grand, interconnected cycle of matter and energy that spans billions of years and trillions of miles. As we pull back from our hypothetical ship, leaving the Scutum constellation behind and heading back toward our modest yellow spark of a sun, we carry this legacy with us. UY Scuti will eventually vanish from our sky. Its light will reach us, tell its story, and then fade into the background radiation of the universe. But the atoms it created will remain. They are in the mountains, they are in the trees, and they are in the eyes of every human being who looks up at the night sky and wonders. The largest star in the universe may be a ghost, but its legacy is written in the very fabric of our being. We are the survivors of the giants, the children of the hypernova, and the stardust that learned to dream. Somewhere out there, around a modest star, life will keep looking up, forever curious about the titans that made its existence possible. The journey to UY Scuti is over, but the journey of the stardust it left behind is just beginning. We've travelled 9,500 light years from the comfort of our modest yellow sun, crossing an ocean of nothingness that the human mind was never designed to navigate. We have peered through the envelope illusion of a star that is more glowing fog than solid sphere, witnessed the rhythmic pulsation chaos of a giant that breathes in the dark, and explored the haunting possibility that this cannibal king only reached its impossible scale by devouring its own stellar siblings. As we pull back from the roiling deep crimson disk of UY Scuti, we are forced to confront a humbling reality. The crown we placed on this star in the early 2010s is currently at the centre of a measurement war, with the Gaia spacecraft suggesting that this titan might be a fallen noble, smaller and closer than we ever imagined, and with new monsters like Stephenson 2-18 emerging from the dust of the Scutum constellation to claim the throne. The leaderboard of the universe is once again written in pencil. But whether UY Scuti is 1,700 times the size of our Sun, or only 755, its true value was never just a number on a chart. UY Scuti exists as a warning and a gift. It is a warning that our models of the universe are still incomplete. that nature loves to break the rules we write, and that the limits of what is possible are constantly being redefined by the next discovery hiding behind a cloud of cosmic dust. But more importantly, it is a gift of perspective. We are a species that lives on a tiny 2-millimeter peppercorn of a planet, yet we have the audacity to measure the girth of a titan across the galaxy. We care about this dying giant because its story is our own stardust legacy. Every atom in your body, heavier than helium, the carbon in your DNA, the oxygen in your lungs, and the iron in your blood, was forged in the desperate, violent heart of a star exactly like this one. UY Scuti is currently seeding the universe with the very ingredients for the next generation of life, hemorrhaging its mass so that one day, around a more stable, modest star, someone else might look up and wonder where they came from. The clock is ticking for the king. Whether it ends its life in a hypernova explosion that outshines the Milky Way or collapses silently into the dark embrace of a black hole, UY Scuti is living on borrowed time. And because of the 9,500-year time lag, that final signal may already be racing toward us through the void. One night soon, or 100,000 years from now, that faint orange dot will ignite, providing a spectacular final show for the inhabitants of a quiet corner of this galaxy. Until that day, we remain the survivors of the giants, the children of the hypernova, and the stardust that learned to think. We are the way the universe has found to know itself. If this journey into the scale of nothingness broke your brain even slightly, or reminded you why we keep looking up, leave a comment below. The conversation about our place in the cosmos is the only thing as vast as the stars themselves. Subscribe to join us on the next flight as we continue to climb the cosmic beanstalk, because in a universe of 400 billion stars, there is no shortage of monsters left to find. Thanks for watching, and we'll see you in the next one.